Fantastic. Hello, everyone. Welcome back to the third edition of our reading group series on interpretable deep learning. Today, I'm very happy to have with us Associate Professor Jean Feng. She's at the Department of Epidemiology and Biostatistics at UCSF / Berkeley Association. And she's going to be here to talk about Bayesian concept bottleneck models with LLM priors. So please, Jean, take it away.
Thanks for having me. And thanks to the organizers. This is a very exciting reading group. Okay, yeah. So today I wanted to talk about Bayesian concept bottleneck models. But before I get to that, maybe I'll just start with kind of motivation, why our group is interested, and kind of just like what our group worked on generally. So half of our group is dedicated to actually trying to build AI models to deploy at the hospital. In particular, we work very closely with the Zuckerberg San Francisco General Hospital. It is a safety net hospital, which means that it serves all patients regardless of their ability to pay or citizenship status or anything. You will get treatment. So we're trying to figure out, like, how do we deploy AI in an equitable way, also in a way that's supportive of the clinical workflow to improve patient health. The other half of our group is developing new research methods, new AI methods, new statistical methods to improve the kind of reliability of these AI models. And a lot of it is done in close collaboration with researchers from the FDA, where we're thinking a lot about kind of regulatory aspects, interpretability, kind of how do they make sure that this thing is reliable, as well as kind of stuff through PCORI, which is like patient-centered outcomes research. Okay, so, and by working on these two different types of angles, one on deployment, one on like research methods development, the hope is that the two kind of inform each other. And so sometimes, or at least increasingly, there are projects that kind of pop up right in the middle. And so this is one of those projects where it was very much inspired by things that we're seeing at the hospital, but we really felt like there needed to be new methodology that needed to be developed. Okay, so with that in mind, I wanted to talk about risk prediction models in medicine. And the most traditional way of building these types of models is where a domain expert, maybe a clinician, will say, hey, I want to predict something. Here are some features that I think are relevant. They give you a matrix of these numbers, and then you just go ahead and start fitting these models, right? You can fit a very simple, say, logistic regression model with an intercept, with coefficients, and you would understand every part of this model. Maybe its AUC isn't the best, but at least you got interpretability. And so this is kind of the process in which kind of these very traditional models are made. The most popular models that are risk prediction models that are used in the hospital are just these very, very simple models. Of course, it's not usually just like a one-time deal. You might fit a model and then the clinician will look at it and be like, can you improve the model further? I actually want to add a few more features here. And so there's this kind of iterative process where they might add or remove some features, they might tweak some stuff here and there, and then we kind of iterate on this process. And in working with clinicians at the hospital, I have learned that there's a fancy buzzword for this called co-design, which I guess also the AI people are very fond of these days as well. Co-design is like generally effective, though it is a very tedious process, right? Like everyone is busy. In between every one of these steps is usually like another 2 to 3 weeks. Okay, so the more modern way that we approach risk prediction models, like in machine learning, is maybe the clinician will just dump thousands of columns from the electronic health record and say, hey, I have these thousands of columns. Can you make sense of this? Give me a model that has really high performance. And that's basically what we've done. You can fit a lasso model. You can fit a gradient boosted tree. We ended up fitting a gradient boosted tree with like 3,000 variables in it. I don't think anyone could truly interpret it. We can give you Shapley values, but does anyone actually know what they mean? The clinicians looked at it and were like, maybe this makes sense, but I'm not really sure. And we also make them a model card just to kind of help in the process. Okay, and then kind of obviously the most recent way people go about building this is, hey, look, we have all this unstructured data, we have clinical notes, we have imaging, let's use all of that. And you could potentially fit a black box model that takes in all of this information, makes a prediction, maybe your AUC gets better than ever. And there are plenty of papers that have kind of taken this path as well. Given we are in this interpretable deep learning seminar series, obviously we know that there's kind of trade-off, right? Like there's this trade-off between explainability and interpretability, and ideally we're actually living in this kind of top corner where it's both interpretable and accurate. And I know many of the recent talks have thought about like, okay, one potential solution to solving this is something like a concept bottleneck model. And so that's actually also the same type of route that our group started looking into. I guess should I review this or should I just continue on with the slides? I'm not sure. I don't know if the audience has heard this like 2 or 3 times already by now.
Up to maybe just like a 15-minute elevator pitch.
Okay, the brief pitch is that, okay, well, we want to do some mixture of black box modeling and very simple kind of interpretability models on top. So if you have unstructured data, like an image, like this bone spur image, or this radiological image, you could try to extract different types of very interpretable concepts using, say, a convolutional neural network, and then you could have a very simple logistic regression model on top, and then that could then your final model and your final features are all extremely interpretable. And the hope is that by having this sort of mixture, you would kind of bridge the gap in terms of accuracy as well. Okay, so just a reminder around kind of how concept bottleneck models are usually trained. Usually you have some domain expert assemble a bunch of concepts for you. Then you have people also annotate a bunch of concepts. And then you train whatever black box model, and then you finally train your interpretable model on top. There are challenges with this, of course. Particularly in certain domains where you don't really have that much prior knowledge. For instance, the task of predicting readmission is surprisingly difficult. It is a very, very noisy outcome, and the features that are relevant probably differ across different hospitals. So it can be quite difficult to kind of pre-specify what set of concepts you actually want to kind of put in your model beforehand. Also, on top of that, in the clinical space, like there are many concepts that sound very similar, but they're actually different concepts. They might have their correlation might be like 0.9, but like they are technically different concepts. So in that world, like you could, in theory, have like infinite concepts essentially. So how are you going to actually pick anything? Obviously, annotation is expensive, and then oftentimes, we still see that CBMs are often outperformed by black box models. Okay, so then the question is like, how can we address this? And so we started thinking a lot about, well, can LLMs actually assist us in this task? And also, I think other papers prior to us were already thinking about this as well. So I think the proposal that many of these prior papers were taking when they were trying to combine these two ideas, which makes a lot of sense because LLMs could potentially assist in a lot of this, was why don't we have the LLM assemble the concept bank? Why don't we have the LLM annotate the observations, these concepts? You already have an LLM that hopefully was pre-trained on a bunch of stuff. It's probably quite accurate. So maybe you don't even need to train a model. And then you just train your interpretable model that lies on top of this whole thing. And here I'm going to use LLM and like vision language models kind of interchangeably. So apologies if that's a little bit confusing. Okay, so then you could kind of go with this procedure. And so it would look something like this, right? So you'd tell your LLM like, hey, I want to predict some sort of Y. Maybe you give it additional context about your situation, and the LLM might suggest some concepts. you ask it to start extracting these values, and then you kind of put together your final model. Okay, but there is kind of this thing that was bothering us, which is that, well, if humans have difficult pre-specifying the relevant concepts, why would an LLM kind of have a lot more insight into this? So then if we think back to kind of the very, I don't know, first or second slide that I showed, maybe we could instead do something like co-design, which is a more iterative process. Like, we know co-design with humans generally kind of gets us models that we like more. Maybe this LLM can help us through that iterative process, even though it might also have this issue of just pre-specifying everything up front. So that means just kind of adding a loop and say, okay, hey, here's some feedback to the LLM. We got an AUC of not very good. Any ideas for how to improve it? And then maybe it'll suggest a new set of concepts. So that makes sense. The question then is, can we make this statistically rigorous? And like, in terms of like statistical rigor, the question is like, are we like gonna overfit? Like, how does one get like uncertainty quantification at the end of all of this? And so that's why we ended up thinking about this idea of kind of putting it all in a Bayesian framing. So the idea is, well, our LLM has some sort of prior around kind of what types of concepts are relevant a priori before it's seen any data, and that prior might not be accurate. But as we kind of, if we do some sort of posterior inference process where we're like searching over possible concepts, then we could have slowly converge to the right kind of region of concepts, hopefully converge to the right ones. And this iterative search process sounds a lot like this co-design kind of iterative process where we're kind of testing out these different concepts. And just as like in Bayesian setups, we don't expect a human's Bayesian prior to be accurate or like completely correct to begin with. Similarly, maybe we could use that kind of framing to say, well, we could use an LLM in that place. Okay, so then just to kind of remind ourselves in terms of how does classical Bayesian variable selection work. I think usually it's called variable selection in that setting because you're working with tabular data rather than kind of unstructured data extracting concepts. But here I'm using variable and concept kind of interchangeably. So Bayesian variable selection, one of the most kind of standard procedures people do is Gibbs sampling. So say you want to fit a concept model or some sort of, say, logistic regression model with only k variables. You predefine a bank of p concepts or variables. I'll stop using I'll use these concepts. There's a bank of like p concepts, and every iteration during your Bayesian posterior sampling process, you're going to maybe let's say k is 3. So you start off with 3 different concepts, and then Gibbs sampling basically takes each one of these and tries to replace them one by one, keeping the rest the same. So maybe you just want to replace that third one, and then you sample from this posterior. So you're trying to sample this kth concept, given the other concepts and all the data. And then you might replace it with some other concept instead. Okay, so that's the most simple like Gibbs sampling process. There's a slightly fancier version of this, Metropolis within Gibbs. In this setting, you have a proposal distribution. And so this is commonly used when you cannot sample exactly from the posterior. So instead, you might sample from a proposal distribution that's simpler to sample from. And then it'll propose some sort of concept and with some sort of acceptance probability, according to this Metropolis-Hastings kind of calculation here, you would or would not accept kind of the proposed concept. And you would repeat this over and over again. So both of these procedures are like, they have good theoretical properties. If you were to run the posterior sampling process forever, then you would converge to the correct posterior. Okay, so then the question is like, can we put LLMs into this? And so actually, this kind of first step where you like have to predefine this bank of P concept is not actually that critical to any of these procedures, so we can just kind of cross out that line, honestly. And we're going to just think about searching over an infinite space of concepts. And then the proposal distribution is something where we think the LLM can really help, right? So like, that's basically what the co-design process is with an LLM or a human. Given the concept you've seen so far, can we replace it with something else? And hopefully it can leverage some sort of prior knowledge or maybe some of the data to help it propose better concepts. But of course, if we were to actually truly adapt this statistical procedure to this LLM context, there's still a bunch of like statistical questions to be answered. I'm not going to go over all of those, but maybe what I'm going to go over is kind of this step, which is really just the most important one, which is like, how are we actually going to propose these concepts exactly? So there's a very simple option. You could conceivably just ask the LLM to propose things without even showing it any of the data. And it's like literally sampling at that point from the LLMs prior. It's like, hey, there are these concepts that exist in the model. What do you think should be the last one? But without seeing any data, and so once it proposes something, then you would just run your accept reject step. But because it hasn't seen any of the data, it's probably proposing things that are not entirely relevant. And so the problem with the good part is this is rigorous, or pretty rigorous at least. In theory, it would converge to that posterior. The problem is this probability, the acceptance of probability, you'll probably end up rejecting it most of the time because just the concepts just don't make sense. It would lead to kind of this acceptance probability being quite small. You can think about this acceptance probability basically as evaluating the goodness of fit of that proposed concept on this kind of held out data. Okay, so then option 2 is, well, why don't we give the LLM access to all of the data that we have and actually try to sample, or tell the LLM, like, do your best to propose from a posterior distribution. Like, look at the existing concepts, look at all the data, just like propose to us what you think that next concept should be. And there are papers that say like, well, LLMs are like approximately doing Bayesian posterior inference. At the same time, these papers also say like, yeah, it's not exactly the same thing. So this is kind of problematic because if you've used all your data, there's actually no data to compute this acceptance probability. You would end up just always accepting this thing. And it's not going to converge to kind of the right posterior distribution that you're actually going after. So this would be biased. You can probably guess where I'm going with this. So option 3 is split the data. So we take some portion of the data and say, hey, you can look at this portion of the data. Oh, I guess I should call this, maybe I should call it train. You can use this portion of the data to propose some concepts. And then we'll use the remaining of the data to actually calculate this acceptance probability. So you can see that this is also very similar to kind of the frequentist setup where we do sample splitting, but kind of in a Bayesian kind of formulation instead. And so hopefully through this, we're getting the best of both worlds, right? Like if the LLM has seen some of the data, it'll hopefully propose some concepts that make more sense, but also are aligned with its prior knowledge. And then we'll also get kind of this fully empirical evaluation of its proposal so that we can fix up mistakes that the LLM has. Okay, so that's basically kind of the mathematical formulation of what we eventually called BC-LLM, Bayesian Concept Bottleneck Models with LLM priors. And like implementation-wise, it goes through these different steps. And I'll just like quickly overview kind of these different steps here. So every round of this is a posterior sampling process, but you do need to initialize a little bit first. So if we take the example of trying to predict some sort of clinical outcome given clinical notes, and we're trying to extract out kind of concepts from these clinical notes, the first step is we'll have the LLM actually just look through these notes and extract some key phrases. So this is just kind of like free-form brainstorming at this stage. And so once you have these key phrases, you can almost think of it as a bag of words kind of representation of each of these different notes. It could be notes, it could be images. You will see later that we also play with images. Then we can actually start our procedure where, assuming you've already kind of initialized your concept bottleneck model, we're going to think about how do we replace one of those concepts. And so you could take your kind of the bags of words and actually fit a bag of words model. And the reason we're doing this is because in theory, like the statistical theory that I have shown you up to now is like, oh, well, we could just have the LLM look at a bunch of data to propose concepts. Honestly, like shoving all the clinical notes into an LLM would be very difficult. So we have this bag of words model to basically provide some sort of summary of what is happening in the data. And so then we would say, hey, LLM, this is like, given these concepts that exist in the model, we're trying to replace the third one. So these are the existing concepts. And then the top key phrases that are associated with the outcome, given these existing ones, are da, da, da. So like it would see, I don't know, for instance, it might see elderly as kind of a top key phrase. 70-year-old is also somehow a top key phrase. And so it might actually look at this and be like, oh, okay, like both of these should probably be combined into a like actual concept that just means like, is this person 60 years old and up? So it's trying to do some sort of aggregation kind of, I guess, like some reasoning on top of this as well. And so like once we provide kind of a prompt like this to the LLM, we would ask it like, hey, can you propose some concepts? And so maybe it would say, oh, okay, I'm going to propose this concept as well as maybe the chest pain concept. And it would also provide some sort of, I guess, its posterior given this subset of the data that we fit the bag of words model on. So given that, then we would actually just go ahead and have the LLM annotate a bunch of these annotate the observations for the proposed concepts. We would then use this to calculate the acceptance probability and then determine which of these candidates we would actually end up picking. I guess in the Bayesian theory, usually people talk about just proposing a single candidate. Here, we realize like out of efficiency purposes, it's much more efficient to propose multiple candidates, and you can do that as well. Okay, so then like every round of this kind of BC-LLM process, you're going to get a different concept bottleneck model. These are your posterior samples. Your final model for making predictions then is, well, what we usually do is just take an average of these posterior samples. Though I guess in theory, you could also just take one of them and use that instead. Okay, so then I'm just going to present some experimental results. So the first experiment we wanted to do was kind of really think through the motivation for BC-LLM was really about kind of situations where we have very limited prior knowledge around what the true concepts are. So to actually do that, we're going to simulate some data. So we took clinical notes from Mimic. Some group has very generously annotated these notes with these 5 different types of concepts related to kind of social determinants of health or just kind of like patient characteristics in general. And we're going to simulate just some outcome Y using a logistic regression model on top of these 5 concepts. And then we're going to ask the BC-LLM, like, hey, can you figure out what concepts in these clinical notes are actually relevant for predicting our Y? So given that we've simulated our Ys kind of like really randomly here, it doesn't have that much context around like what concepts are truly relevant. So this is a pretty difficult task. I guess this was done a little while ago, so with GPT-4 Mini. But you can also, but you'll see that it actually works quite well, even with models that were not super good back in the day. Back in the day, meaning like 2 years ago or 1 year ago. So with 100 observations, this is kind of the type of result you would end up getting. Because we're doing posterior sampling, different concepts will come up. They might come up with different frequencies across the different posterior samples. So here, these are the probabilities of it, or like the prevalences of that concept actually showing up. And then we're just doing some sort of hierarchical clustering of these concepts to kind of just guide our eye in terms of like what types of things is this model ends up sampling. And so this will also give us kind of uncertainty quantification around like, do we have a lot of uncertainty around which concepts are truly relevant? And so this is kind of doing a second layer, right? So usually we talk about uncertainty quantification of coefficients in, say, a logistic regression model. This is going one more meta layer, which is like which concepts are actually in this model, as well as kind of uncertainty quantification around the coefficients themselves. And so with 100 observations, there's a lot of variability in the concepts. The model just like does not have enough information for really recovering the true concepts, though 3 of them are starting to show up. And then with 800 observations is really starting to hone in on the relevant concepts. So for instance, smoking shows up for all of these. They're all kind of very similar concepts, but they are not exactly the same. Like asking the question, is this person currently smoking, is not the exact opposite as is this person a non-smoker or a former smoker, or like, does this person have a smoking history or using tobacco? Those are all slightly different questions. And so it's also unsurprising that the model cannot fully distinguish between these concepts, especially with only 800 observations. But the convergence around this would give us a very good idea of like, okay, generally it's trying to go after a smoking thing. It's also trying to go after some sort of alcohol concept, substance use, unemployment, and retirement. So at this point with 800 observations, we've like we've done pretty well at recovering those true concepts. And then here are kind of the final results. So as we increase the amount of data, you can compare its performance to the different methods. BC-LLM is in blue. Red is Oracle. So we told the model exactly what concepts are the true concepts. So really you just can compare the red line to the blue line. Within, I think this is with 400 observations, it's really catching up to that Oracle method. And it's also doing a better job of like recovering the true concepts. Okay, and then here is the classical cub dataset experiment for evaluating concept bottleneck models. However, we put a spin on this because again, we really want to focus in on the situation where you don't really know what the task is, or like you don't have that much prior information around what the right solution is for this task. So to make this task harder, so if you recall the cub birds data set, there are 200 different types of birds, but they can actually be grouped together into 37 different species, and then there are 200 subspecies within those. So the task is within a given bird species, predict the subspecies. We want to make this different from the typical cub task so that the LLM would not have that much prior knowledge. We're also in the prompts that we give to the LLM, we don't tell it that your job is to predict the bird subspecies. We're just like, here are labels Y, 1, 2, 3, like figure it out. So for all it could know, like maybe we're trying to predict the background. Okay, so here are some examples of little bunting birds. And so just as the typical example of like, this is what the model might end up learning. We also looked at like, oh, what if we put in kind of out of distribution images? Would it kind of be able to catch those? And you can kind of see like this one was kind of funny. This is a picture of my dog. We put wings on it. And then when we asked it, like, does the image contain vibrant feathers? Or like that was a concept it had learned. The LLM wrote 0.5. But it also gave a reasoning, which was like, I see wings, not technically feathers, but they are vibrant. So I'll give you 50% for this concept. So maybe this is all, like the reasoning can also kind of, reasoning and the extractions can kind of help give a hint in terms of like, are you in this out of distribution setting, which is kind of cool. As we have some more experiments on out of distribution in the paper. And then like for this particular setup, we compared it against these other different types of methods. Like there's the non-iterative version versus like the Bayesian iterative process. And then we also compared it against ResNet, which was trained on specifically only the images of the birds within a particular species. And given that ResNet here would have access to fewer images than usual, this black box model, because it's usually data hungry, did not end up performing as well as kind of these like LLM-based methods, which have a little more prior knowledge. Okay, so with that, okay, I'm going to quickly wrap up here. So BC-LLM was very fun. However, and like we actually used it to fit models for the hospital. We showed them the readmission model using BC-LLM, and they were like, wow, this is the first time you've shown us something like actually interpretable. Like compared to the gradient boosted trees that we were fitting with 3,000 variables, they were like, yeah, that was not very helpful. Whereas CBMs, they were like, wow, this is actually cool. But the moment it's interpretable, they also have like so many critiques. They're like, well, I don't really like this. This seems too vague. Like, can you go fix this up? And we're like, oh goodness. So you actually really needed to have like human input into this whole process. So we basically put a second loop around this. And this is a paper that I put on archive under review right now. We've called it human AI co-design for these prediction models, or CBMs really generally speaking. And it's really this iterative process that really needs to happen, where the it could be BC-LLM. Honestly, we ended up putting like a simpler version of concept bottleneck model fitting procedure into this kind of inner loop. But basically, you have some sort of inner loop that tries to fit a CBM to the best of its ability, given the instructions from the clinical team. And then the clinical team can actually inspect the final model. It can inspect kind of the extractions for different patients, and then it can give feedback. And then they can give feedback, and they can redo some of the prompts, right? Sometimes that also might even need to go beyond the prompt. And so we did this iterative process to see like what would end up changing if we allow humans in the loop. And so this is an example. So we did two clinical cases. So one was traumatic brain injury. Another one was predicting acute kidney injury. And so you can see, so in the first round where we had zero clinician input, we just kind of like let our thing run through a bunch of clinical notes. The top concepts learned were like loss of consciousness, which we knew like definitely relevant. It found something like, does this person have a brain bleed, for like predicting or like kind of coming up with a diagnosis of whether or not this patient had traumatic brain injury. Does this person have a neurological event, yada, yada. Anyhow, when the clinicians looked at this, they're like, that's odd. Like, we really wanted to predict traumatic brain injury before an image was collected from this patient, like before a medical imaging exam was done. So you wouldn't really know if the patient has a brain bleed unless you already have information from this imaging scan. So this suggested like there was some sort of data leakage going on, which honestly would have been hard to tell unless you actually fit a model to see that like, okay, some of these clinical notes have this brain bleed information. So then the clinicians had to go back and kind of reformulate the problem. Also, like we ended up like redoing some of the prompts to make sure the LLM wasn't like cheating in any way, so that it was more reflective of what the actual prediction task was going to be. And then we gave them another round, like, okay, here were the kind of revised concepts. And then they were like, well, this coefficient doesn't really make sense. It seems to contradict clinical intuition. So then we modified the CBM learning procedure to be like, you can only propose concepts when or you can only pick concepts where when the learned coefficient actually aligns with the clinical intuition. Otherwise, like clinicians would distrust this type of model. And so you can kind of do these rounds over and over again until kind of the final model where we showed it to the clinician. They're like, okay, we have no problems with this. It looks pretty good. And also kind of our model ended up improving over the different rounds. And these are just some sort of baseline models that are used kind of globally across different hospitals as part of guidelines. Or at least this one's a part of guidelines. This one's just like we tried using open evidence with LLMs to kind of see if a one-time attempt could be good. And kind of this iterative process was both more localized to the hospital and kind of improved the performance over these global models. Okay, so kind of we did the same process with AKI. I don't think I want to go into that, but yeah, so I think that's basically it. So yeah, we have this first version, BC-LLM. We're working on this second version called Hachi. I also want to thank my collaborators. Yan Suo is from NUS, Chandan is a researcher at Microsoft, and then all our clinical collaborators who have helped out on this project as well. And then finally, PS, we're hiring if anyone's interested in working on clinical AI models for deployment. Okay.
Thank you so much. That was fantastic. Are there any questions from anyone in the audience? We have at least 15 minutes, so we can open the floor for questions if anyone has any questions. Yeah, Patrick, go ahead.
Yeah, can you hear me?
Yes.
Okay, great. So first of all, thank you so much for this really nice presentation. I have a question regarding the impact of the different LLMs. So if you could go back to the slide where we have the step 1, 2, 3, 4. Since the LLM is, or real
Oh, you mean, oh yes, you mean something like this?
Yeah, exactly. Since the LLM has a huge impact on the proposal of the candidate concepts and how to annotate those candidate concepts, did you test other models except of, what did you use? You used
There's some of them was BT-40 Mini. Yeah, we did test other ones. So when it comes to like this step, the annotation step, usually it was like, it didn't really matter which LLM, as long as like a reasonably performing one. It's like a pretty like factual question with very limited reasoning. So that one was pretty insensitive. Sometimes it was helpful to have a more powerful LLM to propose candidate concepts. Because that one was like, you got to see this entire list, and then you can think about like, how are they grouping together? How are they related to each other? So that one, there was some influence. At the time of this project, we tried out GPT models, and those are in the main manuscript. And then we tried out some less powerful models. I don't know. I think there were some models from like Anthropic, but there were also some models that were even less popular and are not even really used anymore. And generally, I think the patterns that we saw were similar in the sense that like this iterative process will improve the performance of the model, but like the absolute kind of per family, they can be kind of have varying performance. But within a family, the relative performances of like different CBM procedures using LLMs kind of follow this pattern of like this iterative process was very helpful.
All right, thank you.
Peter, go for it.
Thank you so much for a great talk. I may have missed at some point, but when in this loop would you fit the mapping from concepts to the task? Or do you fit this mapping at every time every time you change concepts, right? But at which stage?
Yeah. It's basically in this step. So prior to deciding whether or not you're going to accept or reject every concept, which concept is proposing, you would fit, like maybe it has like 2 different candidates. you would fit kind of one model for each one of the candidates. Like you take your 2 existing ones and add on this candidate and fit a model, or you would take these 2 existing ones and add on this concept and then fit a model, and you would compare them, and then whichever one is better or gets accepted by your kind of probabilistic acceptance criteria ends up being kind of the one that comes out.
I see. And sorry, I have a follow-up question is, how many iterations do you need to make it converge?
That's a good question. Obviously, there is a financial cost to running every one of these loops. And so what ended up happening is that we don't run the typical amount that you would run for like a true Bayesian inference process. Instead, we tried to leverage some tricks, like really starting the model off at like some pretty good concepts. So doing some sort of like greedy procedure to like pick out some good concepts to begin with. And then from there, we ended up running something like 25 loops, 30 loops. And then generally it looked pretty good. So I wouldn't say that you're truly getting like the posterior distribution, but I think you get a lot more uncertainty quantification compared to not doing this procedure.
I see. And I guess if you allow the clinicians to at least to pre-specify some of the requirements, this would be like the whole procedure might be faster, right? Because
correct. Yeah.
The first guess would be better probably to start.
Exactly. And that was actually kind of the interesting thing. So once we started working with clinicians, we decided like, let's just make the whole thing faster because we just want to iterate with the clinicians much faster, because the clinicians usually improve the model a lot more than the model can like improve itself. Because they'll have like totally different ideas. Like another case study that didn't present, but was also in this kind of version 2 paper, for the acute kidney one, we had taken some set of notes, and the initial prompt that I had written basically was like, look at the patient characteristics, figure out what do you think is predictive. And then the clinician was like, well, like there's two types of factors that you should be thinking about. There's patient characteristics, but also like what surgery is this person getting? Like if we're cutting up the person, like we should probably know about that. And that will tell us if the person's going to get kidney injury. And so like, regardless of however many loops you're going to run, like you really want to like ask the clinician and be like, are we totally off the mark here? So.
I have maybe a follow-up question if no one else has any. Just on that last one, so when you introduce clinicians into the loop, is the sort of interventions that they do is mostly at the prompt level, or is it at the selection level, or both? Like, what is it? Could you just, in theory, at some point, get so good of a prompt that you just don't need the clinician anymore, just can run it as the one that you presented today, or do they always have to be involved?
So there were sometimes we ended up doing things that were not just editing the prompt, because maybe like initially we were running these like iterations, Bayesian or not, to optimize really AUC. But then we realized like, well, maybe we want to, at some point during the project, it was like, well, maybe we don't want to just think about AUC. Maybe we want to think about fairness. So we want some sort of AUC across subgroups that we're simultaneously trying to maximize over. And in that case, or like we want to like reweight the groups or something like that. So then I was like, okay, well, I need to actually change the objective function for you so that we can run this thing better. So sometimes the edits are not prompts, but by and large, we tried to make it easier to use by making it like mostly editing prompts. In terms of whether or not we could move towards something where clinicians don't even need to help, I'm not sure. I think there were some times where it was actually like when a clinician was difficult to reach because they were busy, sometimes I would just like go to an LLM and be like, LLM, go fix the prompts for our LLM. And it would look at kind of past results and be like, okay, here's some feedback that could be useful. And then I would take that feedback and show it to the clinician and be like, do you have anything else to add? So I think as a first draft, I think it can be helpful. And you could even conceivably try to do your best, given an LLM's feedback, try to run enough loops and then show the clinician, be like, you can do like a final pass in terms of like, you want to fix up anything. It's just that sometimes the clinician would really think of something that's totally like out of the box, or like just something very local to the hospital that maybe like a general purpose ChatGPT model might not know about.
Fair. Yeah, that makes a lot of sense. And yes, Peter, go for it.
Sorry. And I'm wondering, like, I guess one of the issues might be that using, as with clinician, like if you ask a single clinician, you may be stuck with like the prior of a single expert.
Yes.
And like in few iterations, you're going to end up with in a local minimum. And I
Yes.
guess the same would happen also with LLMs. I'm wondering whether, like, have you tried diversifying the iterations using different models at the same time, or using an ensemble at each iteration? I don't know. That might be something to explore.
I have not tried different clinicians because then one needs access to many clinicians. What we did do was, though, that like in between, every time we had a new set of prompts, we would run 2 separate seeds so that like there's at least 2 models that end up coming out. So you can see kind of what the stability of the procedure is, and kind of maybe like if either of the directions give some sort of hint in terms of like why you need to update a prompt, maybe you could kind of help use that to get out of a local minimum. But I think I agree with your point that like it can be obviously very sensitive to whoever is actually using the procedure. And like, is there a way to make this somehow more rigorous, even though humans are in the loop? I have no idea.
Right. Jesse, you have a question?
Yeah, hello. Can you hear me?
Yes.
Yeah, sorry, I'm in a bit of a room, but I just wanted to ask, because like for my case, I'm trying to do something similar, but using images rather than text. And a common pattern that I'm finding when talking to clinicians is that they're asking, because sometimes an image might just not be the data in the image might just not be enough to make the final conclusion on what the diagnosis is. And they might, so what they've said is that they will really like the model to just say, okay, this is inconclusive, go for more testing. Has that been something you have faced as well in your model, and how have you been able to address that?
Yeah. I think there are probably multiple ways. For this stuff here, if there's like not enough information, sometimes I'll have the LLM just output a probability instead. But I think there's another way where you could just have the LLM abstain. It's like if you do not know, it could output a separate kind of extraction, being like this is like a missing variable. So we haven't explored that too much. Right now, we're just outputting probabilities, or like LLM to the best of your ability. What do you think this could be? But I think there's probably some research that could be done around there. The other thing that I'm curious, asking a question back to you. We had thought about trying to use this for medical images. I guess maybe probably at the time, it was actually like hard to have LLMs extract very accurately patient characteristics from images. Like you could give it like, I don't know, a lung x-ray and ask the LLM like, is this person, I don't know, is there a nodule or whatever? And the answers did not seem very accurate. So I don't know if you're running into those issues or how you've addressed that.
Yeah, I'm still pretty much experimenting into the field because I'm looking at cancer images and specifically H&E slides from histopathology. But yeah, I'm also finding the same issue of like the concepts extracted from LLM can sometimes be vague, but then also in medical literature, it's not that easy to just find a concept bank that can just rely on. So I think we're just on the same boat trying to figure out what to do. I'm going through the process of looking at the concept bank and seeing what I can improve, and then seeing what concepts can be picked up. But still very much work in progress on my side.
Cool. I'll look forward to hearing more.
Thank
Okay,
you.
is this
We
recording
still have
now?
5 minutes. Yeah.
Okay.
Yeah, it's 5 minutes of time before the shut's on. Sorry, just to follow maybe on something you mentioned. So when you say and this is also relevant to this second step of BC-LLM, those prior values or those probabilities, are those verbalized probabilities that the LLM is given? Like, is it purely like give me a number and I'll take the number?
Yeah, we told it to verbalize it, though I think one could try to think about being a bit more clever about this whole thing.
Oh yeah, no, I was wondering because whether you've tried any of the like uncertainty estimation things, but then that would increase the price as well because usually requires you to do a few. It's like almost just let's see how many times I get the same answer kind of approaches. Okay.
Yeah, I think this BC-LLM paper was really kind of just like for us to set up the foundation, and then I think a lot of these pieces can be swapped in and out for like other things to be improved on. So yeah.
Yes. Cool. Are there any more questions from anyone? Let me see online. No questions on either. Okay. If no more questions, then yeah, thank you so much for being here today and for the amazing presentation. We really appreciate it.
All right. Thanks, everyone. They really enjoyed the questions.
Thank you, everyone. See you everyone next week. Bye-bye.